check, check. That's a reference for my coworkers back home. If you can hear me, just keep your head down in a laptop and keep working. All right. Some people are awake, good. So as Steve mentioned, I'm Carl Kladsky, and I'm going to be talking about the work we did with mitigating Bufferbloat at Comcast. And I'm presenting on behalf of myself, Drew, and Yana. So if this is a well-received presentation, my agreement was all three of us would certainly share the credit. If it's not well-received, then I'll just take the blame because I'm right here. Okay, let's go ahead and get into it. So what is Bufferbloat? I pulled the quote directly from a internet researcher site for bufferbloat.net, and it's basically let me just read it out to you, the undesired latency that comes from a router or other network equipment buffering too much data. So it's basically, we've got big buffers out there, particularly on end equipment. And that's going to, as I'll discuss in the talk, it's going to lead to some interesting phenomena that we want to try and it's not a good phenomena, and we want to take some steps to address it. Memory prices, as we know, in the electronics industry have been dropping down significantly, and we've been employing big buffers in our end equipment, primarily because the benchmark testing and the real-world usage shows the highest throughput out there. And that is a common theme for both vendors when they're trying to sell equipment, and also for service providers as they're trying to make competitive service offerings, talking about trying to get the highest throughput. You know, we can do 150 megabits downstream or 200, whatever the number's going to be. Employing large buffers, particularly in the end equipment, helps to get there. So why do we want to care about this? So I was talking about that throughput. I mean, you see it in every advert for whoever your ISPs are providing competitive service. They're always talking about, we're the fastest throughput, or we're the fastest in-home Wi-Fi, whatever metric they're putting out there on the commercials. It does get you that number, so you get to say, okay, we're excuse me, we're the best in the top line, but it comes as a cost because the additional latency that are introduced as packets are idling in the buffer waiting for transmission. So if you could think of, say, in the upstream direction, we're doing a large file transfer, checking in a whole lot of code or doing something like that, while also trying to run in a real-time application like voice or video. We've got these deep buffers that the file transfer is going to take up, and it's going to fill that up, and it's not going to drop anything because we want to try and maximize that throughput and keep that TCP window open. But then the packets for the interactive applications are sitting there waiting their turn in transmission. That expresses itself as latency to the end application. And if there's nothing in that application that tries to correct for that, I mean, there's mitigation correction techniques out there on that, but there's only so much you can do on a real-time application before you start experiencing, the customer has bad experience, whether it's choppy voice or the game is experiencing lags, talk about a laggy game. So, that's the drawback when we talk about having large buffers in the end device. This phenomenon can happen either in the upstream direction or in the downstream direction or in both directions. So back in the early days of residential internet usage, this is way back, we know, the typical user setup and experience was you've got your modem or your DSL cable modem, DSL router, just one port coming off of that going into your one PC. And it was just one person sitting at the computer, doing whatever activity it was. Typically, if it was something throughput intensive and we got going for the best throughput, the highest throughput, they'd have a good or good enough experience out there. They were the only ones, so that was the, quote, internet experience. Well, that all was well and good when it was one device, but we all know the world has changed around us. We've got all of the new, more laptops, more smartphones, tablets, console gaming, Internet of Things. All of those devices have proliferated out there. And in addition to the types of devices, we also have a different traffic mix, particularly talking about voice and gaming and all of that that's coming over. That breaks the mindset and methodology that was set in place when we're doing these large buffers in the end devices. And that, when you're experiencing latency or gaming lag, that's really just a bummer experience. So what's been done about it? I'll use the acronym AQM. It stands for Adaptive Queue Management Software Algorithms. And they're basically trying to drop packets out of the buffer to strike a balance while minimizing latency, but also still maximizing throughput. You could take a tuning parameter to do it and make things wonderful for latency, but then you'd wind up taking a dramatic hit in throughput. Again, the situation we're trying to correct is get some good experience on latency with minimizing the latency and trying to get good throughput on that. Some of the algorithms that have been developed, the code, it's spelled CODEL, it's pronounced CODL. CODL, FQ-CODL, which is coupling fair queuing with CODL algorithm. Pi, Cake is also working out there. Several algorithms have been developed to address this situation. Pi specifically has been included in the DOCSIS 3.1 standard. So what do we do about it? So over at Comcast, we ran a field trial implementing the static buffer sizes on our DOCSIS cable modems across our network. The AQM testing that we talked about during the development of CODL and FQ-CODL and the work done by internet researchers, a lot of that was done on home routers, people doing stuff on OpenWRTG, on an eThin, Ethernet out router setup. Back over at Cable Labs, which supported the cable industry on the introduction of Pi into the DOCSIS standard, that was all done in lab work. So to the best of our knowledge, we were the first ones to go ahead and try and do some Bufferbloat mitigation technique on the actual cable modem that we would deploy to a customer's home. Well, I know here in the tech group, people probably bringing their own routers or hooking up their own devices to their internet connection, but there's a large population of the internet customers over at Comcast where they're just working with the modem gateway that we give them. So as we look at it, we looked across what was done. We think we're the first ones to go down this path. Okay. Just a brief moment on what's DOCSIS. So the acronym there is the Data Over Cable System Interface Specification. It's the set of specifications from the cable industry that defines the layer 2 packet encapsulation and the layer 1 physical medium transmission over the coaxial copper cable. So that set of standards governs that part of the stack. When you hear about DOCSIS 2.0, DOCSIS 3.0, DOCSIS 3.1, the key takeaway from that is that's increasing higher transmission rates. When we talk about DOCSIS 2.0 compared to DOCSIS 1.0, they increased the channel width. They went from a 3.2 megahertz channel, wide channel, to a 6.4 megahertz wide channel. And then when the DOCSIS 3.0 came out, they introduced channel bonding across those 6.4 megahertz channels so that you get, again, higher throughput, higher transmission rates. And then finally, what's happening now with DOCSIS 3.1, they're introducing OFDM channels to, again, try and increase the usage of the spectrum to get more throughput through that. AQMs, they're not particularly dependent on DOCSIS, but in terms of managing this through the industry and how to get it work with our vendors and get this deployed, the cable industry linked it up with the DOCSIS 3.1 standard. Again, there's nothing that's, it says AQM and DOCSIS 3.1 are tied together, but it was an inflection point where we were doing changes to the requirements and changes to the specifications, so it was a good fit to put that in there at that point. So how did we do this field trial? So when we talk about on a particular modem that we have deployed in our network, we were able to adjust the cable modem buffer size in fixed values. Only the upstream buffer was able to be adjusted, and the default was from the vendor was a 96 kilobyte deep buffer. We had then done, in addition to taking baseline measurements at the 96K, KB, we'd also worked down to 48 kilobyte and 8 kilobyte buffer sizes to basically see what the effects and impacts was this really going to be able to mitigate the buffer bloat where we were having good throughput but not so good latency. We had enlisted a whole bunch of our existing customers to host the modems in their home. In addition, this was separate from the modem they were using for their regular internet service. So we sent them another modem and basically a Banana Pi where we had them hook it up through the Ethernet port of that and run testing with the Banana Pi. And it was all automated. They didn't have to do anything. They basically just had to plug it all in, get it set up, and make sure the lights came on. We had a test suite that would basically run, and I'll talk about that in a moment, and the results are basically just SCP'd back to our server. Okay, wait a minute. I was just talking about AQMs, and I was talking about Pi and DOCSIS 3.1, and added to that. All that is true, and that's all where we want to go, but at the time we were doing this experiment in the early part of the year, the DOCSIS 3.1 modems were not available yet. So we wanted to try and do something and see if these in general, if the buffer bloat mitigation techniques would work. They hadn't been, we haven't received 3.1 modems, and we hadn't done any work with them on the 3.0 modems for the AQMs, and that's why we did this. I'll call it a static buffer management. We're talking about adjusting the buffer at fixed sizes. So what did we do in the field trial? We were using a test suite from, it was developed open source called Flint, which is basically a wrapper around NetPerf that helps run some CAN tests. And it's part of the RRUL test suite, and RRUL stands for Real-Time Response Under Load. The methodology of measurement on buffer bloat is basically to maximize maximize your throughput while also doing a latency check. So that's the wording behind RRUL. I list the links there if you want to get the code or take a look at that, play around with Flint as a NetPerf. It's a pretty good tool for measurement. The CAN tests that we ran were basically doing a unidirectional latency checks while doing the unidirectional throughput run. And this was all automatically generated. We've just set it off to run at particular times of the day that I'll talk about. And then we didn't have to intervene manually for the test. We did downstream latency under load separate from upstream latency under load. We were not trying to do it all together. We still don't see that model where upstream and downstream are utilized fully at the same time in our footprint, so we were able to just kind of contain and bound some of the variables that we're looking at in this trial. So how did we do this? Again, we were running 3 times a day. We did 8 noon and 5 p.m. all UTC time, and that's across all of the probes. So regardless of geography, where the probe was in our network for the trial participant, it was running at the same time of the day. So in the east, of the probes that we had out there, for example, noon is 7 a.m. because East Coast is -5 off of UTC, while in on the West Coast, it was minus that, 3 in the morning. 3 in the morning for, I think they're 8 off of UTC, if I got the math right on that. But we're running them uniformly at the same time. We were not trying to adjust for any local time. We conduct this over a 3-week period, and each week we were changing the buffer size. So we talked about the 3 buffer sizes of 96 KB, 48 KB, and 8. We'd set the modem, reset it, set it with a particular value, make sure the modem took the change, and then left it alone for a week to run the tests. Then the second week we changed down to the next buffer size, same deal, reset the modem, make sure it all took, let that run for another week, and then finally the third week of the same. When we talk about these throughput tests that were generated by NetPerf, they're all run into a centrally located server in Westchester, PA. So again, the East Coast and West Coast and central part of the country probes were all going to the same server. We had worked with about 50 people, but due to some equipment problems and some cabling problems in a couple of the participants' homes, we probably had about 45 consistent trial participants over the 3-week period. So what were the metrics we were looking at? We looked at throughput in terms of the mean of the data streams average. We're looking at latency, of course, for the mean of the UDP ping round trip time. And for the given metrics, we were looking at a statistical construct referred to as percent delta. And what that means is that it is a measurement, a comparison between the observation at a particular time to this on a particular probe to the average for that probe over the whole 3-week life cycle of the test. So for example, for each test run, let's say the 8 a.m. Monday test run on week 1, we would compare that result against the average of the entire, for all the readings for that probe over the 3 weeks, to come up with a percentage difference on how far away from that average a given reading was. So how do we go about analyzing this data? We had verified that the 3 weeks experiment, we tried to do a check that nothing else dramatic was happening on the network, if there was any maintenance or anything that. And the way we did that was we had 2 additional data sets to compare against. One was from the Sam Knows Measuring Broadband America program. I don't know if people are familiar with that one, but that's a FCC-sponsored test where they put basically a probe in a customer's home, and it's across multiple ISPs that are doing that. So we had access to the ones that the Comcast customers were running. We also had access to the customers running speed tests to the Comcast speed test server customers, and we have that tool out there so customers can take a look at their own data throughput just for their own benefit. We looked at those 2 things and said, okay, nothing that we were seeing on the trial participant probes was out of line with what's happening on the network, so we were confident that there wasn't any routing issues or there wasn't any other phenomenon going on that would have impacted our results. The model fitting we did was we had each of the target variables. We did a fitted linear regression to determine the significant predictors and which were not significant predictors. The target variables we talk about is percent delta. Again, this percent delta we computed for upstream latency, upstream throughput, downstream latency, and downstream throughput. And the model predictors were the week number of the test, because we had the 3 different weeks where we were doing different things, the day of the week, and the time of the test. We went in with the null hypothesis, which is saying is that if there was no differences among the 3 weeks, then the week should not be a significant predictor for the percent delta, meaning if this wasn't working, we should just see a random pattern of this across the 3 weeks, and we should not be able to pick anything discerning out of it. So that was our methodology going in. What did the distributions of the percent delta look like? So I show 4 charts here again. The upstream throughput percent delta, the upstream latency percent delta, downstream throughput percent delta, and the downstream latency percent delta. And one of the benefits of using percent delta is it allows us to give a comparison across metrics that have different units. So we're actually able to see a comparison between throughput, which is expressed in megabit, measured in megabits per second, and latency, which is in milliseconds. By looking at this, converting to this percent delta attribute, we're able to look at that, which is a dimensionless unit, and just do the comparison against there. So some of the things that you'll see in the upstream chart, which is where we had expected most of our impact to take place, is if you look on the coloring scheme there, the brown is the first week where we had the lowest buffer size set at 8 kilobytes, excuse me. The middle blue is the 48 kilobyte measurement when the buffer size was that, and then the pink or fuchsia, whatever color that is, was the week 3 with the 96 kilobyte buffer size. You see on the throughput, you see that box plot there, and I had my cheat notes on box plot with me. Iana is our data scientist and gave me the crash course on these. The top, when you see that width of the box, what that represents is the lower bound of that box is the 25th percentile reading. The upper line is the 75th percentile. And then the thick black line in the middle of that represents the median, where half of the readings were above that line and half were below. When you look at the throughput, you see that for that week 1, you see some deviation off there. I think we're bouncing ranging between 0 and minus 20%. So that represents there was that range of throughput degradation as compared to the other 2 weeks. Another point, when you look at the upstream latency, which is the lower left graph, again, the right box, the brown box, shows the range of latency, and you see that's down there at minus 20 to minus 40% delta. So the way that you look at that and saying the readings from that period were between 20 and 40% off of the average across the probes of that 3 weeks. So it's kind of telling you something that there's some impact out there on that. And you look at the, again, at the lower left chart, so the week 1 results were below the percent delta, had a negative percent delta. The second week, which is the 48 kilobyte buffer size, was right about the 0 mark, so it was little to no deviation on there. And then the third week shows the positive percent delta, which represents changes over a higher latency compared to the whole average across the whole period. Then as you look at the downstream, we don't see a lot of deviation across that, and they're pretty close to the 0 line. So this is looking to see, we were starting to see things we wanted to see. We're seeing impact on the upstream in terms of throughput and latency, and no impact on the downstream because we're only making adjustments to the upstream buffer size. So what were the results of this? So in terms of any form of significant predictor, the upload throughput, the week 2 was 14% higher than week 1 for throughput, and week 3 was 14% higher than week 1 also. The download throughput you saw was just 2% lower than week 1, and week 3 was 3% lower than week 1. It's negligible impact there. But then on that bottom line latency, which is what we were going after, we see week 2 was 27% higher than week 1, which means it had more latency than week 1. And then week 3 was 63% higher than week 1. So the trend line, as you see it, is that lower to higher buffer size is trending an impact on lower to higher latency. So what were the results of this? So none of the predictors on the download were significant for download latency, really no impact on there. We also were able to see that the day of the week and the time of the week were really not significant predictors on any of these as we did the analysis on any of this. So that really just left us with the weeks, the difference between week 1 and week 2 and week 2 and week 3, and comparing those against each other. That's where we saw the difference. And that aligns with our expectations because, again, we were changing the buffer size across each of those weeks. So what does this tell us? So the upload latency did show the expected pattern, is that the increased buffer size was showing a higher average percent delta latency, those same numbers I just went through on the prior chart, and that the upload throughput with the week with the lowest buffer size has the lowest average percent delta, and we did expect to have some impact in the upstream throughput because, again, we're talking about a trade-off between this fulcrum between throughput and latency. It's kind of like two sides of a seesaw. We're trying to hit an ideal point on that, and so the fact that we saw some impact on the throughput in the upstream direction is in line with our expectations. So what is this all telling us? So there may be a trade-off there, but it also doesn't seem to be linear. So if we were to go ahead and do a deployment of this, we're kind of looking at this and say, really that sweet spot is that 48 kilobyte buffer size. So you get improvement in the latency, but less of a hit on the throughput as you would on the 8K, but again, seeing improvement over the 96K buffer size. So, going at that, if we're to try and do a large-scale deployment, that kind of would be our sweet spot. Okay, so what happens next? We talked about this was the static buffer size control. Really, we're going after AQM, which is the adaptive queue management, but it gave us a measure of optimism that, yes, Bufferbloat mitigation techniques can work on our real equipment, not just in the lab, equipment in customers' homes, running in, in controlled fashion, but it was at least in their homes, it was outside the lab. That was a data point I needed to get for our senior leadership so that I can continue forward into the AQM size of it. Unfortunately, the fixed buffer size setting, the work that we did, it's kind of impractical to do at scaled usage. If we had to scale that up to the millions of subscribers that we had, it really would be impractical because we had to do adjustments to the configuration files, which were just not burdensome and had to be done manually. I mean, yeah, we could automate some of it, but it still would break some of our provisioning models. So the fixed buffer size setting, it was good because it gave us an experiment where we could see the positive impact of the Bufferbloat mitigation, but it's not there for scalable. We're continuing to work with the DOCSIS 3.1 modem and modem and CMTS vendors to implement Pi AQM. Now, the specifications were written so that implementation of the Pi AQM algorithm was a must for the modems and a should for the CMTS. Now, what that translates to in reality is that the CM side is a must and the CMTS side gets ignored because the vendors, as soon as you see a should requirement, well, we know how that goes. The must get done, the shoulds get forgotten about. In addition to the work that's being done on the DOCSIS 3.1 modems and CMTS, I'm also have a separate side project to try and retrofit FQ-Coddle AQM into our DOCSIS 3.0 modems to see if we can get somewhere on that, because we do have a large deployed base of them, and maybe there's some impact we can have. So that's still work in progress too. So that gives you an overview of what we did on Bufferbloat mitigation. We felt pretty good on this whole trial and what came out of it. We leveraged all of the work of the industry internet researchers that have worked on this. A lot of people across a lot of time have spent a lot of time on this. I'm not going to name drop because I'll probably wind up forgetting somebody important, and I don't want to do that. So let me just say a big kudos to all of the researchers that have worked on Bufferbloat. If you do any internet searches, the common names that you pop up are the people that I'm talking about. And I think that's my last slide. Are we available for questions if anyone has any? Hi.
Jeff Houston. Fascinating work, and it's really good to see this kind of work happening inside real networks as distinct from in laboratories. The work we've always thought about, though, is that the buffers that sit inside switching elements in networks interact with the end-to-end protocol behavior. And the early work done on buffer behavior was all about TCP Reno. This whole idea of most of your traffic was additive increase, multiplicative decrease. Mm-hmm. The optimal buffer size was meant to be twice the bandwidth delay product of the line you're driving.
Yes.
And Van Jacobs did a huge amount of work back in the 80s, and this was the accepted theory. Since then, Reno is dying a death, we've noticed. And there's an awful lot of things like cubic and even other forms of TCP flow control, which tend to be highly delay variation sensitive. And what happens then, of course, is when the buffers start to fill, they immediately back off in their pacing algorithm of sending to even avoid the buffer in the first place. So it's not quite, I can just change buffer sizes and the world will alter, because the world is busy changing its end-to-end flow algorithm. So my question to you is, have you ever thought about instrumenting some of those DOCSIS modems with real users and real traffic to actually understand what happens in your DOCSIS modems today, as distinct from a banana pie running some TCP algorithm that you have, which is not quite the same as what users have? How much insight do you have into what we do as customers on your network and through those modems?
So what we've been looking at is, along with the implementation on the 3.1 modems of Pi, is to get better view into the buffer usage. In the current generation modems, we don't have that metric available. As we introduce that Pi, we're asking the vendors to give us that reading so we can statistically look and say, how much sizing, what's going on in there, and then use that as feedback into whether we need to do AQM work on the modems or on the CMTS, or look at other things like TCP BBR. That's another, beyond Cubic and beyond Reno, there's TCP-BPR. They're having a paper on that come out here in October. On that doing its sender to client, server to client, it's doing a bandwidth bottleneck measurement and a round trip time measurement and trying to reduce the congestion window that way.
Exactly. And if the world was BBR, would you even worry about the size of your buffer, given the fact that BBR is trying not to put packets in the buffer in the first place?
That's a question that we have to address, because this was a long time coming in terms of getting it on the modems and getting somewhere. And just as we're on the cusp of getting there, somebody's got potentially a silver bullet out there. So I've been monitoring that community to see that, and I'm also trying to set up an experiment on the Comcast network to see the impact of BBR. One outcome might be that on the server side that we do TCP BBR, but then still do to cover the downstream buffer bloat mitigation, while still running some form of AQM on the modem for the upstream, and kind of use those two pieces as an overall solution.
Thank you.
Welcome.
Okay, we're at time, but let's go ahead and have one or two questions. Go ahead, continue.
I'm going to interpose. I'm going to QoS Mr. Seastrom down a notch. Is that okay, Rob?
Hey, as long as you don't drop me.
Oh, okay. We're deep queue here. So thanks for mentioning BBR, Jeff. My name is Anton Capella, 5'9". I'm curious for the speaker, what interactions have you maybe seen in your experience, or have you specifically looked at interactions of, call it loss rates, that are not queuing induced, interacting with your good work on queue control? Specifically, DOCSIS upstreams, as you know, I mean, I'm not familiar with 3.1, but I don't suspect you've added a sequencing or hybrid ARQ layer magically in there. So we can transmit from the modem, right, and think it's going to get to the CMTS, and it doesn't go back up the wire out the other end just fine, because something, impulse noise or ingress or otherwise, knocked it out, right? But we're counting against those entries as if they got successfully transmitted. So we have a queue that does have a known loss rate if we oversubscribe it as the user's perspective, right? And BBR and things seek to minimize that effect. But then we have this other loss process that is not the stochastic randomized process. It can be very much not stochastic, as we know in the physical layer. What's going on, if there's anything considering that, call it physical layer mid-span, which we control pretty well in LTE, by the way, and other mobile protocols that are challenging environments to deal with, which we don't address here, to my knowledge, yet in DOCSIS.
And unfortunately, that's still the case. I'm really not aware of any work where we're trying to get that loss rate back on the CMTS or that measurement point. So that's an excellent point taken. That's something I can bring back to the to the cable industry.
I'd love to invite you to that, because we have Category 6 chipsets in our phones today that are consuming under a watt, doing 300 meg downlinks, 100 meg uplinks with ARQ, with sequencing, and this problem is pretty minimized there. I'd love to see that on a wireline network. I think a lot of operators would. Thank you.
Sure, thank you. Let's sync up afterwards. I'll get your contact and follow up.
Hi, Rob Seastrom. I have my badge off to remind me to say Charter Communications. I couldn't help noticing that the times that you stated that you did the tests tended to be times I'm either in bed or not in the house. Did you do any testing at peak hour where there might be more contention for upstream transmission slots, and what did you find?
Unfortunately, we didn't do any testing at peak times. That part I'd say we could probably do a better experiment design on our next go through, but unfortunately, no, we didn't. We know that peak times, obviously, right after work when people get home, that window, and then it changes over the weekends. Unfortunately for this experiment, we really didn't get a view into that. When we go out and do experiments with Pi AQM, I want to do a better comparison on peak time, because we have the data on when the peak times, and you guys know too. But that has to be for another experiment. Unfortunately, we didn't get that.
Thank you.
Let's thank the speaker, Carl, again for a great talk on experiments in their real live network. Thanks, Carl. All right, next speaker up is Ron Woodward.